Hi everybody, today we're going to have a look at sets. A set's a collection or group of elements that can include numbers, letters or other objects. Typically we call the set of all elements we're going to be considered the universal set, or we can call it a sample space. In the case of the universal set, we'd call it with a U. In the case of a sample space, we'd usually give it an S. We commonly use a Venn diagram to show how elements in a sample set are related. And how they're distributed across sets. So in this case, we've got two sets, set A and set B. Set A is going to be in the red circle, set B is going to be in the B circle. This region here in the middle, and that's where we're going to put elements that are in both sets. Out here, we'll put elements that are neither in A nor B. Elements that are only in A we'll put in this region, and elements that are only in B we'll put in this region. There are four regions, 1, 2, 3, and 4. Now how these all relate to each other is easier seen in a sample. So we're going to consider only integers from 1 to 10. So our sample space is only going to have numbers from 1 to 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's our universe. Now we're going to let set A be all the even numbers in our universe. So 2, 4, 6, 8, 10. And we're going to let set B be all the prime numbers in our universe, or in our sample. 2, 3, 5, and 7. All the other numbers are composite numbers, or 0, or in our case 1, because we're not counting 0. So let's put these sets into our Venn diagram. So in A we want 2, 4, 6, 8, 10, 2, 4, 6, 8, 10. And in B we want 2, 3, 5, 7, 2, 3, 5, 7. And we can see that we put 2 in the middle because it's in both sets. All of these numbers are either in A only or in B only. Which leaves us with sad old 1 and 9, 1 that's neither prime nor even, and 9 that's a composite number, which is neither prime nor even. So they're neither in set A or B, but they are in our universe. So all the elements that we're concerned with from our sample have been included in our Venn diagram. And now we can name the different parts in the different regions. In A only are these numbers, 4, 6, 8, and 10. In B only are these numbers, 3, 5, and 7. In both A and in B is just the number 2. Not in A or B, so not in our circles, is 1 and 9. In A itself, as we said earlier, are all of the red numbers, all the numbers in the red circle, 2, 4, 6, 8, and 10. And all the numbers in the B circle are 2, 3, 5, and 7. Now that's not the only way we can use a Venn diagram. We can also use it to show how many elements are in each region. So, as we can see over here, in the whole red circle, we have 5 elements. 1, 2, 3, 4, 5. In the whole blue circle, for set B, we have 1, 2, 3, 4 elements, which we've got here in the little dog ear. In B only, we have 3 elements. There they are there. And in A only, we have 4 elements. And in the intersection, there's only 1 element. So here we've got a recording of the counts of how many elements are in each region, 2 being on the outside. And over here we show how to list it. So the number of elements in A only is equal to 4. The number of elements in A only, this is the A only region, is 4. The number of elements in A and B is 1. The number of elements in B only is 3. And that's where these counts come from. So if we're trying to show a count, put a little n in front to say how many elements are in it. Now once we understand that, we can use the counts and the total number of elements, which we write outside the box, or the sum of all the elements would be 10 in this case. In this case, this doesn't really have a meaning, so I'm going to get rid of that. Not quite sure that's a valid place to put it. Well, this says I've got 10 elements. It's actually the sum of each of the regions. So 4 plus 1 plus 3 plus 2 gives me 10. And I can use that to work out the probability of choosing an element for various regions. The probability of choosing a region, an element from A only would be 4 elements out of 10. For the intersection would be 1 element out of 10. For the B only segment, it would be 3 elements out of 10. And for none of the above, it would be 2 elements out of 10. And if I add these fractions up, they're going to add up to 1, just like a normal probability set would do, because it counts all possible cases. If we're trying to show that, the probability of A only would equal 4 out of 10. In the same way, the number of elements in A nor B would be 2 in this case. Now, these natural language type representations, A only, B only, A nor B, can be a little bit messy, so we have mathematical symbols to do the same job. So in the case of this region here in the middle, A and B, we can use A intersection B, which is an upside down U symbol, and say at A intersection B. If we meant the whole region, or the whole three regions, A only, A and B only together, we can use the OR, which just means to union them together or combine them all. And we would use this U symbol to indicate a union. So A or B, if it's in A or it's in B or it's in both, we're doing a union B. If we wanted everything not in the A region, this is the complement of A, and we denote it either with A prime or A with a bar over the top. And if we wanted A only, we would say everything that's not in B together with the intersection of A. So not in B would be all of this region out here. A is this. Where the two overlap is this region here, A only. And we can then find the count for it, find the probability for it, just by making sure that we can name how to identify the elements in it. Which leads us to the last major region. We have this region outside of the two circles. So if we had a definition for inside the two circles, which we know is A union B, and we took the complement of that, that would be everything outside the two circles. So if we're looking for the A nor B region, we could say it as not the union of A and B, or the complement of A union B. So let's consider the earlier sample space. I've summarized it in these three diagrams. So if we're wanting to find set A, we could look at the red circle, the whole circle for A, and that would give us 2, 4, 6, 8. The intersection would be 2. A and not B would be A only. That's 4, 6, 8, and 10. Everything not in A would be 3, 7, 5, 9, and 1. So there's a little bit of an error there. I can get rid of that 10, make it 1. Oops. There we go. And everything not in A union B would be 9 and 1. If we're looking at number of elements, there's 5 elements in the A circle. Got that in the doggy here as a summary. In the intersection, there's 1 unit. In A only, there's 4 elements. In not A, there's 5 elements. And in not B, there's 6 elements. And not in the union, there are 2 elements. If we're looking at probabilities, the probability of choosing an element in the A set would be 5 out of 10, 1/10 plus 4/10. In the intersection would just be 1 out of 10. In A only would be 4 out of 10. In not A would be these two combined, which would be 5 out of 10. And in the outside region, in A nor B, or in the complement of not the union, would be 2 out of 10. Finally, there is another way of showing the content of two sets, and that's to use a two-way table. If we have a look here, what the two-way table shows is the intersection of whatever's in the row headers and the column headers. So the intersection of A and B, the intersection of A and not B, the intersection of not A and B, and the intersection of not A and not B. And they relate to these regions in the Venn diagram. So this would be A and B, this would be A only, this would be the outside, this would be B only, this would be the sum of B, this would be the sum of A. And if you look at this table here, this Venn diagram here, it relates to the numbers in this two-way table. B only is there, the the intersection is there. Sorry, A only is here, B only is there, the intersection is there, A nor B is out here. The count for all of B is there, the count for all of A is there. Quite easy to work with, a little bit harder to explain. And that's a brief summary of sets, and it will help when you're attempting the exercise. So there you go. Any questions? Don't forget to leave them underneath. Thank you, everybody.